and once again, a very good evening to all my students, especially for the our section 1 and also the section 2 for the subject of the Human Factor Engineering or HFE. Okay, so today our lecture, we are continue our chapter 2B. Okay, chapter 2B. So we talk about the our biomechanics. Okay, so the previous class we have been talk about anthropometric. Okay, so right now we are talking about the biomechanics chapter. Okay, so we can see here what is a biomechanics. Okay, have you heard any word regarding to our biomechanic in a real industry? Any word you hear about the our biomechanics? Oh, bio is not a biological, This is but a biomechanics. So what is a biomechanics? So by definition, a biomechanic is science concerned with the mechanical behavior of the musculoskeletal system. Okay, so I repeat again. By definition, biomechanics is defined as a science concerned with the mechanical behavior of the musculoskeletal system. So what is musculoskeletal system? So later on I will explain. And component tissue when physical work is performed. So we call it as a biomechanics. Okay. In simple word, biomechanics is provide understanding of basic of manual activity in the industry. Okay. So how do we lift, lower, pushing, pulling any load or objects. And then when we look at on the definition by Cromer in 1987, the definition by biomechanics is a major assumption of the occupational biomechanics is the body behave according to the law of the Newtonian mechanics. So by definition, mechanics is a study of the force and their effect on the mass. That's why we also have the Newton first law, second law, third law, and other things. And biomechanics is an interdisciplinary field in which information brought from biological science, okay, with the engineering mechanic in order to assess the function of the body. So we can say that combination between in biological science and also the engineering mechanic. So that's why we call it as a biomechanics. Okay. And this is the law of the motion. Okay. So this is just a recap. So if you learn about the physics, Newton first law is a body that originally at rest will remain at the rest, or a body moving with a constant velocity in a straight line will maintain its motion until external resultant force is applied. So this is our Newton first law. So don't worry about this, our Newton first law. Later on we do some of the exercise. Meanwhile, for the inertia is a tendency for the body maintain its state of the rest or the uniform motion in the straight line. So the more inertia an object has, the harder is it to start moving from it the rest. Okay, so this is Newton first law, and this is inertia. And Newton's second law stated that acceleration of the body is directionally proportional to the net force acting on the body and inversely proportional to its mass. So this is second law, okay, law of the motions, okay. Previously is a Newton first law, okay. This is second law. Meanwhile, the third law for the Newton, for every action, there is an equal and opposite reaction. Okay, so we are using first law, second law, third law in order to calculate our biomechanics. So what are the goal of the biomechanic assessment? So we want to quantitatively describe the musculoskeletal loading that occur during the works. So that that one can derive appreciation for a degree of the risk associated with the occupational related task. So this is our goal of our assessments. So we want to quantify what are the musculoskeletal loadings that occur during a works. Okay, and we need to look at on degree of the risk associated with the occupational related tasks. So more on the biomechanic or manual handling activities. And then the study of the physical interaction of the worker with their tools or machine or material so that to enhance the worker performance while minimizing the risk of the musculoskeletal disorder. Okay, so this is our the study of physical interaction. Okay, so we want to double check whether interaction between worker with their tool or machine or material, is it comfortable? Is it fit to the man's? Okay, for example. And this is a biomechanical concept. The first one, we learn about the load tolerance model. Okay, in which this is a fundamental concept. A design workplace so that the load imposed on the structure does not exceed the tolerance of the structure. So we look at on the example. Okay, this is a graph for the X is the time and Y for the loads. As you can see here, if the tolerance far exceed the load, so it meaning that the task is safe. Okay. So if we have a load here, okay, and if the tolerance far exceed the load, we consider the task is safe. Meanwhile, uh, but in biomechanic logics, with repetitively loading, okay, the tolerance of the structure of the interest may decrease over a time. Might be decreased over a time. Okay, and sometimes we result in injury or illnesses. Okay, so this is how the load tolerance model in logicals from the our biomechanic perspective. And in second concept, acute versus cumulative trauma. Okay, what is acute? What is a cumulative trauma? So acute trauma is an application of the force is so large that exceed the tolerance of the body structure during an occupational task. Meanwhile, the cumulative trauma is a repeated application of the force to the structure that tend to wear it down. Okay, so in simple words, cumulative is repeated application of the force. Okay, meanwhile, for the acute application of the force in large that exceed the tolerance of the body structure. So this is how between different between the acute and the cumulative trauma. So this is number B, the biomechanical concepts. Meanwhile, the other concept is about the movement and lever. So biomechanical load not defined by magnitude of the weight supported by the body. Okay, so not defined by magnitude. Okay. Meanwhile, for the movement, is the position of the weight relative to the axis of the rotation of the body joint. Okay, this is more on theoretical. So later on, we'll do some of the exercise regarding to our biomechanical concepts. Okay, this is an example. We have a first class level. We also have the second class level, third class level. So the first class level, this is number one. Whenever the axis is located between the motive force, okay, and the resistive force, the level is of the first class. So let's say this is efforts. Okay. So this is a load apply. And also we also have a fulcrum or pivot point. So for example, look at on the our scissor here. So when we apply the force from the top to the downs, so this is fulcrum and the load will be on the upwards. So this we call it as a first class level. Meanwhile, for the second level, okay, second level system, whenever the rotary component of the resistive force is located between the rotatory component of the motive force and the axis. So the level is the second class. So the effort comes from the bottom to the upwards. And load here, fulcrum here. For example, This is second class level. So we apply the force from the bottom to the upwards, and the load will be here. This is the fulcrum. This is what we call a second class level system. Meanwhile, for the third class level system, so whenever the rotary component of the motive force is located between the axis and the rotary component of the resistive force, so the level is third class. So meaning that the efforts has been applied and load will be here and fulcrum or pivot point will be here. For example, like this. This is, we call it a third class level. So this is our elbow is a fulcrum. This is applied force will be here in our elbow. And this is a load. This is what we call it as a third class level. So you have to differentiate between first class level, second class level system, and also the third class level system. So in biomechanical concept, we divide by three type of the class level system. And for the D, external internal load. So external load refer to those force that are imposed on the body as a result for the gravity acting upon external objects. Meanwhile, internal load refer those counteracts force to maintain the equilibriums. Okay, so this is what we call it as an internal and external load. Okay, so external load is a force imposed on the body result for the gravity. Okay, upon and the external objects.
Hari
So
73.
meanwhile, for the our internal load, we refer
Eh,
to
asal Ricky
counteract
kau
force to
tekan?
maintain equilibrium. Tu siapa pula tu? Terdengar suara? Ah. Okay, this is a example concept. How do we calculate the force? Okay, external, internal loading. So let's say they are given to you, this is bicep force, Fi. So the given distance 2.54 centimeter and distance between this elbow point to the our arm, okay, hand is 30.5 cm. So the load applied will be 44.5 Newton. So calculate the force. So from the our basic concept, okay, the moment will be 0. So put force here, okay, times 2. Okay, this is force here, times with 0.0254 meter here. Equal, okay, same concepts, okay. The force will be here, 44.5 Newton times with 0.305 meter. Put it here. So we need to find the force. So in order to find the force, okay, we have moved our 0.025 4 meter will be down here, and we calculate, we get the 534.35 Newton. So this is the force. Okay, so this is basic concept. Clear? Any question? Tadi ada suara,
No.
tolong mute okay, good. Okay, please apply this example I give it to you. Please calculate the force. So the moment will be 0. Okay. So the force, okay, internal loading, for example, times to convert centimeter to meter. So what do you get? 1 cm equal to 100 meter, right? So convert 1.2 cm times, okay, divide 1 meter 100 cm, right? Oh, sorry. Sorry, mistake. Okay, 1 meter 100 cm. Is it correct? Okay, so we divide 100 cm here. Okay, or cm. Okay. Okay, 1 meter will be here. So meter, meter. So what do we get? 0 point? 0 point? Please give me an answer. 0.127 or 0.0127?
0.0.
0.0127.
0.0127.
Okay, equal to uh, 44.5 Newton. Okay, 44.5 Newton meter. Okay, Newton okay, Newton times with 15.25 cm. Convert to meter. So we will get 0 point 0.152 5 meter. Okay, I'm sorry. Okay, here. In order to get the force, internal force, okay, Fi, okay, so 44.5 times to 0.152 divided by 0.017. So what you get the answer for the force? So what the answer? This calculator, please. This is basic. 44.5 times to 0.1527. 525 divided by 0.0127. So how do we get?
534.35.
0.35 unit? Newton or meter? Newton. Okay. So let's say we cross here, Newton, Newton. So meter, meter cross here. So only left a Newton. So this is how we calculate the force for the internal and external loading, especially for the biomechanical concepts. Okay. Okay, we move on the next slide. Okay, this is structure and function musculoskeletal system. So you might be ask me, doctor, what is a musculoskeletal system? This is our first time heard about the word of musculoskeletal system. So the function of musculoskeletal system is a support and protect the body and its organ. And also the function of musculoskeletal system is to provide a motion. So this is basically our structure and function of musculoskeletal system. Ah. So this side is a bone, this side is a muscle. Okay. So all these things we call it as a musculoskeletal system. So in other words, musculoskeletal system is made up from the body bone, such as skeleton, muscle, okay, cartilage, tendon, ligament, joint, and other connective tissue that support and bind tissue and organ together. So the primary function including supporting a body, allowing a motion, and protecting a vital organ. So this is how the structure and function of our musculoskeletal system. Okay. And then we look at on the detail here. Okay, musculoskeletal system including the muscle. Okay, the red one is a muscle. Okay, we also have a cartilage. Okay, we also have the bone. Okay, tendon, joint and ligament. Okay, this is our main structure for our musculoskeletal system. And this is our bone human skeleton. We have skull, clavicles, scapula, okay, rib cage, humerus, spine, pelvis, ulna, radius, femur, patella, tibia, fibula. Okay, so this is a structure of the bone human skeleton, or we call it as a musculoskeletal system. So from the basic musculoskeletal system, again, I repeat again, made up from the body bone, skeleton, muscle, cartilage, tendon, ligament, joint, and other connective tissue in order to support and bind tissue on the organ together. So this is our musculoskeletal system. And this is structure, okay, major substructure, tendon, okay, ligament, fascia, cartilage, bone, muscle, joint, a lot motion between body segment, okay. So this is musculoskeletal system. So if you learn about the connective tissue matrix, collagen fiber, okay, we have divided by three types. Type number one, type number two, and type number three. Type number one include the tendon, ligament, bone, and skins. Meanwhile, type number two, cartilage. And last but not least, type number three is the blood vessel walls. Okay. So mechanical properties depend on the fiber type and fiber arrangement. Okay. So this is connective tissue matrix. And when we look at on the tendon structure, okay, tendon shape. So we have a synovium, lubricant producing a tissue. Meanwhile, we also have synovial fluid, lubricant fluid. So this is tendon structure. And tendon also and ligament, a certain point, ligament surround part of the tendon to act a pulley, okay, as a tendon guides. Meanwhile, for the ligament attachment, allow tendon to work around the corner as a finger and toes. Okay, for example. Okay, this example, tendon, muscle to the bone, okay, and ligament, bone to the bone, okay. So this is our structure, eh. For example, tibia, femur, okay, so the leg, eh. Okay, and then the other type, cartilage, three types. Okay, this is more on the biomechanical, so you have to understand the basic concept of musculoskeletal systems. So what is the cartilage? It's important structural component of the body. So the firm tissue, but is softer and much more flexible than bones. So cartilage is connective tissue found in many areas of the body, including a joint between bone, elbow, knees, ankles, and of the ribs between the vertebra in the spines, or ears and nose, and bronchial tubes or airways. Okay, so all these things, this is cartilage, three types. Okay, and the other things, okay, I don't touch about the detail for the cartilage type, okay. So the bone, 99% of the body calcium is the bone, okay. 80% of the bone tissue by weight is the mineral, okay. Bone group by axials, okay, long bones, okay. So axial, particular bone, flat bones such as a skull, pelvis, rib, vertebra. Meanwhile, for the long bone, this is extremis, round bone compressive, the pieces shaft, okay, pieces to expanded of the end. So we also have a type of the bone, coaxial and cancellous, compact bone and spongy bones, okay. And we look at on the our skeletal muscle. Skeletal muscle is 50% at least body weight. Okay. Skeletal muscle is strained a strip and excluded a cardiac and smooth muscles. Several hundred muscle in the body. Okay. Skeletal muscle in under voluntary controls. And each muscle is separated by the organs. Each muscle attached to the bone by the tendon across one or more joints. And generally, skeletal muscle generate movement about the joints. Okay. Uh, so this is basic. And meanwhile, for the properties of skeletal muscle, so we have a basic concept. We call it statics, isometrics, or dynamics, isotonics, construction. So what is different between isometric statics or in meanwhile versus with the isotonics? Isometric is a muscle contract to change a muscle tone without changing a length. Okay, so they can increase the postural stability. Meanwhile, for the isotonic dynamic, it's a muscle contract to the change of the muscle length. This produces a movement of the joint. Okay, so between dynamic contraction, increase the blood flow to the muscle with slow fatigues. So this is the properties of the skeletal muscle. Okay, we look at on detail. So in ergonomic, the main problem, okay, in issue related to our manual handling is about the lower back injuries. So in order to get to learn about the biomechanics of the lower backs, so this is our main topics. Okay, focus on the lower backs. Okay, what's the force of the spine? Empirical study and biomechanical analysis has shown that mechanical stress is a factor in injury causations. Okay, the lumbar spine. Please remember the word lumbar spine is the particular interest as the LBP, lower back pain. It's the common in the workforce. So that's why many workers in industry have claims also regarding to the ergonomic issue related to our musculoskeletal system. And this is focused on the first number one, the workers industry claim in SOXO, the first ones is caused about the lower back pain, LBP. So this is lifetime prevalent is more than 80% in our LBP, a force of the spine. Okay, this is basic. This is correct way. Okay, in order to manual handling, we have to squatting. Okay, properly. Okay, and bend and straight with your knees and instead of your backs. Okay, in line. Okay, do not bending posture. Uh, the bending posture can cause of the seriously injuries regarding to our PID lumbar, especially for the L5 and S1. Okay, and this is a biomechanical spine models. Okay, we call it as a head. What is a head? So the back muscle must produce a movement of the force to counteract movement from the hand force and the weight of the head, arm, and torso. So otherwise, person bend forward. So this is what we call it a head. Head. H-A-T. H stand for the head, A stand for the arm, and T stand for the torso. So when we apply the hand force will begin here. Okay. So if they have a force here, so this is a force for the our torso, and we start to calculate our muscle movement will be like this direction. So this is how we can produce the person bend forwards. Okay, this is a biomechanical spine model. The concept for the head model is simplest from of the upper torso is modeled as a single mass representative for the head, arm, and trunk. Okay, so that's why we call it as the head. Trunk also known as a torso. Okay, trunk also have a known as a back, your back. Okay, although simple to analyze this model, obviously have limited accuracy. Whether we apply the head model is very simple, but they have a limitation on the accuracy in order to calculate this using head model. For example, this is a moment of the force. Okay, so the moment of the force is tendency of the force applied to the object that cause object to rotate about the point. Okay, let's say moment or magnitudes equal to perpendicular distance. Okay, D here. Okay, need to time with the force. Where the force will be there. So the formula of the moment is D times to df. Okay. Okay. And then the load movement will be here. So the moment of the force will be measured by the Nm, Newton meter. Okay. So let's we begin on the our example. Okay. Where's our example? Okay. Okay. Example for the simple head movement model. Okay. So let's say if the question given to you, this is what we call is a D distance or LP. Okay, LP is a distance between load. This is load. Okay, okay. This is our torso. Okay, okay. Example, and this is simple calculation. And they given to you LP. LP is stand for the our distance between a load from here to the our center of the our load here. From the load to the torso. Okay, and then they give it to you 200 Newton. Okay, let's see. How do we calculate the moment from our simple calculation here? This is the answer, forward moment bending. This is they given to you the answer, also the answer. So how to calculate the movement? So apply this formula, moment, okay. For the first thing, moment, distance times to the force, okay. So distance, we will say that 20 cm. 20 cm, please convert to the meter. So if we convert to the meter, we'll get 0.2 meter. Okay, so moment, so 0.2 meter here times with the force. Force applied is 200 Newton. So how the number that we get for the moment? Calculate please. So the moment will be 40 Newton meter. So please refer here. Correct. Okay, simple head movement model. Meanwhile, for the our second example, this is movement due to load only. Please take note. Okay, 40 cm convert to the our meter 0.4 meter. Okay, times with 200 Newton. So what the moment will get? 80 Newton. 80 Newton meter. 0.4 meter time with our distance, our load 200 Newton. So the moment that we'll get here is 80 Newton meter. Okay, so this is basic things, simple head model, but it's not accurate. This is just a basics, the rule of thumb. Okay. Okay, we look at on the our spine definition. Okay, what is L4, L5, or L5 S1? Have you heard anything from our previously? L4. Okay, if you go to the medical, you see the medical doctor. So medical doctors saying that after you do the MRI, magnetic resonance image for your backbone, so they printed, say, then they can conclude that your L5, S5, L4, L5, or L5, S1 have degenerative disc, or for example. Okay, so biomechanical model of lifting show the large movement are created in the trunk, especially a load cannot be held for the close. So between 95% to 95% to 85% to 95%, all of the disc hernia occur relatively equally at the L4, L5, and L5 S1 level. So some model they are using L4, L5, and the another model they are using L5 S1 model in order to calculate the biomechanical lower back pains or LBP. So the disc between L5 S1 incur the greatest moment in lifting. So one of the most vulnerable tissue to force-induced injuries. Okay, so this is how degeneration disc for the our intertrabal disc. Okay, L5 S1. So this is L1, L2, L3, L4, L5. So we want to look at between L4 and L5, and or we want to look at L5 and LS1. Uh, so each of our normal anatomy, okay. So this is what we call a spinal cord. Okay, this is spinal cord. It will be here. So this is our what we call is a disc. Okay, this will be here. Okay, so we want to look at whether this is a normal disc, degenerative, or bulging disc, and others conditions. Okay, so this is our L4, L5. So we want to look at every what are the condition of this between L4, L5? Is it condition of the disc bulge, for examples? And we want to look at on L5 and S1. Okay, is it hernia? This with a compression of a left for the spinal cord. This is spinal cord. Is it compressed with the spinal cord? Okay. This is example generative generation of the L4, L5, and also the L5 and S1. Okay, this is the MRI. Okay, if you do MRI for your lower back, okay, this is interpretation. Okay, the figure will be like this. So we want to look at whether L4, L5 is a good condition or L5 in between and S1 is good conditions. Okay, so this is our location where this left side hernia, okay, bulge of the L5, S1 disc. Example, this is a view for the our superior view L4 L5 disc, okay, from the top. So we want to look at whether the disc touch to the spinal cord in order to get the our lower back pain degeneration disc. And compression, shear torsion. Okay. Okay, NIOS suggests that a maximum compression is 3.4 kilonewton. Okay. So this is from the NIOS cross-sectional field study. Provide estimate for the compression force generated by lifting tasks, biomechanical modeling, and subsequent injuries. Okay. From their study, Herring study 55 jobs. Okay. So 2,834 potential stressful on the manual material handling tasks. So trace medical record 6,912 workers were involved. So the four job comprehensive of between 4.5 until to 6 to 6.8 kilonewton. The rate back problem was is for 1.5 times greater than for the job with the compression less than 4.5 kilonewton. So it's all related to manual material handling, including lifting the load, lowering the load, carrying the load, pushing, pulling, heavy load in related tasks. Okay, so this is a compression force. What we call is a force to the due to the back muscle compression. Okay. So in our spinal nerve code, okay, this is L4, this is L5. So this is a force FM. FM stand for the muscle force. Okay, force due to the back muscle. So we want to calculate here. So this is erector spine and others. Okay, so the example, if we have the our different of the our distance, more distance can cause of the more forward movement for the bending. Okay, so you can see from here, if we are bending more times and bending with more time with a distance too far, can increase our movement of the our bending movement. Okay, so this is different between a normal condition and also the bending forward conditions. These things. So how do we calculate the biomechanical model for the lower back? This is cantilever lower back model of lifting by Cheffins. Okay, as you can see here, this is muscle force. We also have a muscle compression force. We also have a force for the shear force. And we also have DB. B stand for the hour from torso, okay, from the hour movement. And meanwhile, for the hash torso, distance between torso distance between our load. And this is our mg load here. So how do we calculate these things? Okay, I will give the example. So in order to calculate the movement from this our low backs, we also have the formula. So the moment is a load to torso. Okay, load to torso equal to weight of the load, okay, times to the hash, okay, plus, okay, weight of the torso itself times to the B. So where's the A and B? A and B, A, B, A, hash and B. So where is the hash and B? Hash will be distant from the load to our torso. Okay, these things. And meanwhile, B from the our torso to our force. Okay, from our shear here. Okay. So later on, we do some of the exercise. Okay. Okay, this is an example, simple head movement. Okay, define a muscle movement. Okay, the given LW will be here. LW, okay. LW stand for the our B, okay, distance between body center and the torso. LW or B. Meanwhile, we given to you LP. LP is a distance between load and the torso. Okay, so calculate, find out the muscle movement. So from our formula here, movement, okay, okay, if we are going to force B, okay, forward bending, okay, will be, uh, please follow this formula, follow this formula. We just put into our value. So weight load. So what is a weight load that we have here? 200 Newton, right? Ah, okay, 200. Okay, Newton. Okay, times 2. Look at on distance. Distance LP or distance LW. So we need to look at on the LP. Distance between load and torso hash. Okay, so hash we consider LP. LP. Oh, hash here. Okay, so we call it hash. Hash here. Oh, and B will be here. So convert to the our meter. Why do we need to convert the meter, doctor? Because we want to find out the our Newton meter. So if we convert to meter, we will get 0.23 meter. Okay. So please 0.23 meter. Okay. Bracket here. And then plus. Uh, plus what are the weight of the torso? Weight of the torso given 450 Newton. 450 Newton. Okay, times with LW. So LW is B. Okay, please follow the formula. So in cm 0.05 meter. So 0.05 meter. Then we will get the moment will be. Please do the calculator, please. Please use the calculator in order to calculate the moment for the force forward bendings. Okay, moment for the forward bending. So how will you get the number?
68,45.
Okay, 68.5 Newton meter. So we'll check here the answer. Okay, 69. Okay, can be 69. Okay, if we make a nearest one, 69 Newton meter, for example. Okay, so this is how we need to find out the movement, the muscle movement. Okay, using the head system models. Okay, any questions so far? Clear? This is basic thing, basic, static, dynamic, Okay, so please look at the basic. Okay, look at a free body diagram. Okay, so sum of the Fy. Okay, also is 0. Ignore arm ignore arm weak. Okay, this is arm segment. 200 Newton will be here. 200 Newton will be upward. Okay, in which this is trunk segment. If you look at on the trunk segment, compressive force will be starting here. This is a shear force. Okay. And then they give it to you the rate, the moment force or muscle, not muscle force is the rate one. Okay. And when we look at on the shear force component in the blue color, okay, this is a blue color. Okay, meanwhile the compressive force is pink. Uh, okay, so when we call it as a compressive force, it will be here. This is certain of degree. Okay. Okay, this is some example how we want to find a muscle movement and muscle force and also the compression and shear force. Okay, so I give it to you the example. Okay, the complicated example. Okay, please look at on the our example here. Okay. Okay, this is body system static model. Okay, we have a two-dimensional back model. Okay, same goes to be previous one. Okay, force compressions, force shear, force muscles, and also we have the B, hash, mg. Okay, for the center of the body, and mg for the load. Okay. Okay, when we look at on this, for example, if we are giving a question, okay, assuming lifting occurring a mid-sagittal plane, we want to estimate the back muscle force, F muscle, okay, spine compressive force, F compressive force, okay, and the spine force shear, at the moment of the lift, when the body angle are similar as shown as above, so we also assume only erector spine muscle is sole provider of the counterbalancing movement during this lifting. So no other back arm muscle are significantly active. So we are also assuming that force for the shear force is resistant by the passive resistance from the joint capsule and ligament at the spine. So all these things are given to you. So the load in the hand, okay, this is example. So load in the hand 450 Newton. Uh, okay, they given to you here. Upper body weight above L5S1 joint 350 Newton. Okay, load, okay, 450 Newton. Okay, upper body weight. Where's upper body weight? Here is about 300. Is about 350 Newton. Okay. And then give it to you E. E is distant erector spine muscle from the center of the spine. E. Which one? E. 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 E here. Distance between here. Okay, they given to you 6.5 cm. Okay. Hash. Distance the load from the center of the spine. 30 cm. Hash. 30 cm. Meanwhile, for the B, distance from the upper body center gravity from the center of spine, they give it to you 20 cm. 20 cm. Okay. And alpha, okay, upper body angle with horizontal 55 degrees. Alpha, look at here, 55 degree. So how do we calculate to determine our muscle force, our compressive force, and our shear force? Okay, so please take out all the data. So you know the mg load 450 Newton, our body weight load is 350 Newton, so the B distance 20 cm, H 30 cm, and our degree of the bendings alpha is 55 degree. Okay, solution to find out internal force, we cut the upper body bisection perpendicular to the spine. And show all the internal and external force acting for the upper body. So cut up here, as I mentioned earlier. Okay, this is distance 6.5 cm. Okay, muscle force. Okay, muscle compression. Force shear force. 55, 55 degree. Okay, alpha. Okay, okay. This is okay, horizontal. Okay, for the horizontal. Okay, look at on our first things. Okay, 55 given to you. Okay, so why do we get a 35 here? 90 degree minus to 55 degree. So we also have the 35 degree. Okay. Okay. Give it to you 350 Newton, 450 Newton, 30 cm, 20 cm. Okay. The first thing you have to do is taking a moment around L5S1 joint and equating is 0. So we get moment uh, will be 0. So muscle force times to 6.5. Okay. Okay. Minus to 350 Newton times to 20 minus to 450 Newton times to 30. So we will get 0 here. In order to get Fm, okay, or we get the Fm here, so you have to divide again. 350 times 20 plus 450 Newton times to 30 cm divide by 6.5 here. So we will get the muscle force will be 3,154 Newton in downward. This is the first thing. Okay, clear? So taking the moment is 0. Okay, equating to the 0. So we'll get this muscle force will be 3,154 Newton downward. So that is a muscle have produced of the 3,154 Newton force to maintain in static equilibrium. Okay, clear? Understand will be here? Okay. Then look at on our second things. Observe task for this example, the muscle force is approximately 7 times the force at the hand. Also observe then when picking up the same load, if the upper body lean forward, so the muscle force will be increased as a zero moment arm of the force will be increased. Yes, correct. In by theoretical. Okay, when we look at on detail, this is very detailed. We get the here our FM. Muscle force 3,154 Newton will be here. So how do we calculate the our force for the shear and force for the compression? So please draw like this. Ah. Okay, so they're given to you. This is our 350 Newton. 350 Newton. What are the force? 350 Newton. A body weight here. 450 is our load. Okay. This is our load. This is our center of body weight. Okay. So please put it here. In by theoretical, if we are in segment of the lower back, okay, we'll have the 55 degrees here. Okay, this is where the 350 newtons, where the other 201 Newton, 287 Newton, we look at on our previously question. Okay, they given to you. Given to you. Okay, don't worry. How to calculate here? Okay, to find the spine compressive and spine shear force, we resolve the body weight and the force hand into X and Y component, where Y direction is being parallel to the spine axis. Okay, so we start to calculate FB. Okay, FB stand for the our body weight force for the X direction. Meanwhile, for the our what we call it as a uh, force for the our body weight for the Y direction. So please put it on this FBW cos alpha for the X. For the Y, FBW sin alpha. So calculate here 350 FB. FB will be 350. Okay, will be here. Okay. And then please uh, please do using a calculator. 350 cos 55. Alpha is 55 here. They given to you alpha. So we will get 201 Newton. 201 Newton, put it here as our x axis. Meanwhile, for our y-axis, for our body weight force, 350 sin 55. So we will get 287 Newton will be here. Okay. Uh, I'm using a different color. Okay, green color. Okay. Meanwhile, for our load for the force FL, for the direction X and Y, same goes to be previously. FL cos A alpha, FL sin alpha. So please put it on this 450 here. Okay. Uh, cos 55. This is 55 degree. So we will get for the X will be 255 Newton will be here. Meanwhile, for the y-axis, for our load force will be 369 will be here. Okay, clear. So first thing, before you need to find our spine compressive and spine shear force, we have to resolve the body weight force into X and Y component direction. Okay. Then after you get all these things, okay, does equating force in Y direction, wait, okay, in Y direction, for let's say our force for the Y is will be 0. Okay, so our compression force will be like this. So please, 3,154 plus with 287 plus with 369. So we will get the force for the x direction 3,810 Newton. Meanwhile, for the x direction, force shear, okay, this is force compression, this is a force shear. So we'll get 201 plus 258. So we'll get 459 Newton. Okay, this is how we calculate the compression force, and this is how we calculate the shear force. Okay, clear? Uh, any questions so far? Any
Clear.
question? Clear? Okay, good. Thus, what is the conclusion behind it? The spine compressive force is about, okay, so we divide 3,800 Newton will be here, divide by our 450. So mainly 450 will be here. This is our normal load, okay. So when we divide, so it meaning that's 8.5 times the load with the hand. So based on our epidemiological study have shown that the higher occupational spine compressive force is strongly correlated with incidence of the lower back pain. That's all. Okay, I pick up on the color. Okay, so please find out the compression force, the shear force, and also how to we calculate our muscle force. Okay. Okay, clear. Okay, if you are clear here, okay, we are going to stop our recording video. Okay. Okay.